Hello again. In this section we're going to focus on what are called one-sided limits. We've actually already talked about this concept, we just haven't really introduced the notation for it. Because when we were finding limits in the previous section, we talked about things like from the left and from the right. And that's exactly this concept of a one-sided limit. And so let's introduce some notation for it, get some practice understanding what we mean by a one-sided limit. Alright, so it's a similar notation. The basic idea is that if for the left-hand limit, if x is approaching c, we used a in previous sections, well, whatever, it's the same concept. If x is approaching some number from the left, the notation we use is limit x arrow c, and then we put a little negative as a superscript in where we'd sort of think of the exponent normally. Okay, and so this little negative says we're approaching c from the left. Now, if we're approaching a number from the left, if you think of your number line and you think of, okay, here's a number line and here's c. If we're approaching from the left, that's what we mean by when we're approaching from the left. So if we're approaching from the left, that means that our x values that we're using, our inputs, are less than c. All right, so x is less than c if we're approaching from the left. If we're approaching from the right, so the right-hand limit, the notation is limit x approaches c, and we put a little positive in the superscript on the c. So, all right, so now if we're approaching c from the right on our number line, that means that these values, our x values that we're thinking about, are greater than c. All right, so this is a key thing to remember. If we have a one-sided, not 3c. So this is a key thing to remember. If we have a one-sided limit, if we're approaching from the left, that means we're using values less than our c value. And if we're approaching from the right, that means we're using x values that are greater than that c value. Let's see an example or two of this. All right, so here's an example. We have a function. It's a piecewise defined function defined in 3 pieces. The function is defined as x minus 4 if x is less than 1, 2x plus 5 if x is between 1 and 3, and x squared plus 2 if x is greater than 3. Alright, so the first thing we're asked for here is to find the limit with x approaching 1 from the left of the function. Alright, so again, what does this mean? This means that x is less than 1. And if we're approaching 1 and x is less than 1, we think, okay, this is a number that's really close to 1, but like on the left of 1. So maybe this is like 0.999, right? Something like that. That would be a number that's less than 1 and close to 1. All right, so if this were my x value, it's pretty close to 1. And if I'm approaching from the left and I'm less than 1, then I would be following the first rule, right? The x minus 4 rule. And so if my x value is pretty close to 1, then x minus 4 should get pretty close to negative 3. Right, because a number close to 1, subtract 4, that's going to be close to negative 3. All right, now, the limit with x approaching 1 from the right of the function. All right, so if I'm approaching from the right, then x is greater than 1. So I'm thinking like, okay, maybe it's 1.0001, right? It's a number like that. It's a number close to 1, but on the right-hand side of 1. All right, so now, if I'm greater than 1, but I'm close to 1, then I should be using the 2x plus 5 rule. All right, so using the 2x plus 5 rule, and And if x is getting close to 1, 2 times 1 is 2 plus 5 is 7. All right, now what about the limit with x approaching 1 of the function? Well, what I see from the previous steps is, if I'm approaching from the left, I get one value, -3, but if I'm approaching from the right, I get a different value of 7. This indicates to me that this limit, as x approaches 1, does not exist. The left limit and the right limit are different. The limit at 1 does not exist. Now, what about f of 1? Okay, so that means now f of 1 says the input is exactly 1. If the input is exactly 1, then we would use the rule that contains the input exactly 1. And so we are following the second rule, the 2x plus 5, letting x equal 1. This would again give us 7. All right, let's consider this next set of exercises. Similar set of exercises, but now focusing on x approaching 3 and x equaling 3. All right, so if x is approaching 3 from the left, all right, so that means that x is a number that's close to 3, but on the left of 3. So I would use the 2x plus 5 rule, because that's where x is less than 3. So then 2 times 3 is 6 plus 5 is 11. All right, now the limit with x approaching 3 from the right. Now here this means that x is greater than 3, close to 3. Now if x is greater than 3, then I would follow the x squared plus 2 rule. So that's 3 squared, that's 9 plus 2 is 11. All right, so the limit with x approaching 3, since the left limit and the right limit are the same, this limit would also be equal to 11. Now, f of 3. All right, so we look at f of 3. Hey, now remember, this means that what is the function value when the input is 3? Well, if we look at our rules for this function, it's defined if x is less than 3, and it's defined if x is greater than 3. This function is never defined if x is equal to 3. F of 3 is undefined. There is no part of this rule that says that there's an output when the input is 3. Now, graphically, we would see this as an open point when x was 3, probably. All right, so here's another example. It's a similar type of exercise. I would like for you to pause and try this one out on your own. All right, so we again have a function defined in 3 pieces. It's defined as 1 plus x if x is less than -1. It's defined as x squared minus 1 if -1 is less than or equal to x is less than or equal to 1. And it's defined as 2 minus x if x is greater than 1. So here we're asked to find the limit as x approaches -1 from the left. Be careful with the notation. X is approaching -1 from the left. So here, x is less than -1. If x is less than -1, then our output would be following the 1 plus x rule. 1 plus a number close to -1. 1 plus -1 is 0. If x is approaching -1 from the right, here x is greater than -1. Following the x squared minus 1 rule, -1 squared is 1. 1 minus 1 is also 0. Since the limit on the left and the limit on the right of -1 are the same, the limit at -1 is also 0. F of -1. All right, f of -1, if the input is -1, we would follow the x squared minus 1 rule, and again, that is equal to 0. All right, now, what if x is approaching 1? If x is approaching 1 from the left, so this means here that x is less than 1. If x is less than 1, I'd be following the x squared minus 1 rule. And so that would be 1 squared minus 1. That is, again, 0. If x is approaching 1 from the right, here x is greater than 1. Here I'm following the 2 minus x rule. 2 minus 1 is 1. The left limit and the right limit are different, so the limit at x, as x approaches 1 does not exist. And f of 1, if we're trying to evaluate f of 1, my input is exactly 1. I would follow the x squared minus 1 rule, which is 0. All right, so that's how we can work with the notation. There's a couple of symbolic examples. Let's look at some examples where we are given graphs instead of the actual function notation. All right, so here I took this exercise from the Paul's Notes pages. And here we're given this function. It looks like a step function, right? It's different levels, different steps. All right, so here we're asked for each of the given points to determine the value of f of a, the limit with f approaching a from the left of the function, and the limit with x approaching a from the right of the function. If any of these quantities do not exist, clearly explain why. All right, so let's see. F of negative 1. If my input is negative 1, I go to the solid point. That would be 4. The limit with x approaching negative 1 from the left of the function. If I'm approaching negative 1 from the left, my output is approaching 4. Limit with x approaching negative 1 from the right. If my input is approaching negative 1 from the right, my output is approaching negative 2. Why don't you pause and try these other two examples on this page? All right, if a equals 1, f of 1, going to the solid point when my input is 1, f of 1 is negative 2. The limit as x approaches 1 from the left of the function, 1 from the left, the output would be approaching negative 2. Limit with x approaching 1 from the right of the function. As I approach 1 from the right, the output is approaching 3. And notice in both of these cases, if we were to ask, and it wasn't asked, but if I was to ask what's the limit as x approaches negative 1 of f of x, we would have to say that this limit does not exist, since the left limit and the right limit are different. And same with if a is 1. All right, what if a is 3? F of 3. F of 3 is 1. The limit with x approaching 3 from the left of the function. As x approaches 3 from the left, the output is approaching 3. And if x is approaching 3 from the right, the output is approaching 1. Okay, so just reading the graph carefully. All right, here's another example. Now would be a good time to pause. Try this exercise out on your own. All right, and I won't write down all the notation for these. F of a, if a is negative 3, f of a, if a is negative 3, the output is 5. The limit from the left, if I'm approaching negative 3 from the left, the output is approaching 2. If I'm approaching -3 from the right, again, the output is approaching 2. In this case, again, we weren't asked for this. We could say that the limit as x approaches -3 of the function is 2, since the left limit and the right limit are the same, even though the function isn't defined as that value. All right, if a is -1, the output is 4. The left limit, if x is approaching -1 from the left, the output is, again, 4. If x is approaching -1 from the right, the output is approaching -3. And again, if we were asked for it, we would say that the limit as x approaches -1 of the function does not exist. If a is 1, all right, so if my input is 1, the function f of 1 is undefined. F of 1 is undefined. As I approach -1 from the left, as I approach 1 from the left, x approaches at 1, the output is approaching -1. And as I approach from the right, the output is again approaching -1. So the left limit is -1, the right limit is also -1. And finally, if a is 2, then the function output is 0. The left limit, as I approach 2 from the left, the output is approaching 0. Now, as I approach 2 from the right, what's happening here? As I approach 2 from the right, is there a clear output here? So what that looks to me is, as I'm approaching, the values are oscillating repeatedly, getting close. As x is approaching 2, the values are oscillating. It keeps moving up and down. And so I would say that the right limit, I'm going to be careful with the notation here, I'll go ahead and write it out. The limit with x approaching 2 from the right of this function does not exist. All right, when we see that oscillating form like that, we cannot define the limit. All right, let's take a slightly different approach here. And now here we're asked to try to sketch a function that meets certain conditions. So here we're asked to sketch a graph of a single function that satisfies each of these conditions. So we are only allowed to draw one function, and it's got to meet all these conditions. The limit as x approaches -5 from the left of the function is -1. The limit as x approaches -5 from the right of the function is 7. The function evaluated at -5 is 4. The limit with x approaching 4 of the function is 6, but f of 4 does not exist. All right, so now would be a good time to pause and see if you can draw a function like this on your own. And then I'll come back and draw one. I guess I should say that my answer might look different from yours, but it should have some of the same characteristics. All right, so let's see what we got here. We are told that I'm going to start with this. I'm going to start right here. We're told that f of -5 equals 4. So that means I know I have a solid point. I have at least one point on the curve. If f of -5 equals 4, that means that the curve has a solid point at 5, 4. I know that much. Now let's go back to the first part here. The limit with x approaching -5 from the left of the function is -1. All right, so I'm approaching -5 from the left. I'm approaching -5 from the left. My output is getting close to -1. Let's put an open point at -5, -1. Now I've got to my curve has to actually approach that value. So let me draw a curve that does something like that. There's a curve that approaches that value. However, the limit as x approaches -5 from the right of the function equals 7. So again, as I'm approaching -5 from the right, my output is getting close to 7. Let's put an open point at -5, 7, and let's draw a curve coming off of that from the right. The limit as x approaches 4 of the function is 6. Now, let's understand what this means. Since the limit as x approaches 4 of the function is 6, that means that the left limit and the right limit as x approaches 4 is 6. So on both sides of 4, the output is getting close to 6. However, f of 4 does not exist. So I can't put a solid point at 4, 6. I must put an open point at 4, 6. But my curve has to approach that on either side. And I'll just go ahead and connect here in the middle. So here is a function that meets all of those conditions. It's not the only function that does this. Here, I'll draw another function in purple that does the same thing. So this is, let's call this f of x, right? Black is f of x. And here in purple, here's another function. Here in purple, there's a different function f of x that meets those same conditions. All right, so there's actually, there is not just one answer. Now, something that would be bad, what would be something that would be incorrect? Here, I'll draw in red something that would be incorrect. What if I did this? What if I changed the part in between and I did something like this? Let's put a little loop in it. This would not be correct because it's not a function, right? This is not a function. All right, and then other bad examples would be, if it just didn't meet those conditions, if you mixed up the solid and the open points, things like that. All right, so I apologize if that's a little bit of a mess, but I wanted to kind of give you an idea that there's not just one right answer to an exercise like this. There might be many correct answers, but they should all have some of the same characteristics. All right, so that completes this topic on one-sided limits. Then what we're going to do next is we've been working mostly with, kind of the idea of close to, and let's substitute numbers, inputs, maybe using a calculator. But there's actually some other ways that we can evaluate limits using symbolic, using analytical techniques. And so we're going to introduce some of those ideas in the next topic. I'll see you then.